actually, all right, that'll be good. So can you actually see my screen now? So this presentation mode. Yep. Yes. All right, that's good. First of all, actually, thank you very much for for Mike and also Yelu inviting me to give a talk at this webinar. I'm going to talk about the GeoNEX Earth observation from operational geostationary satellite sensors. I mean, obviously, this is a team effort from many of my collaborators at NASA Ames, also across the nation and actually all over the world, from Japan and Korean, and also from China. All right, so this is going to be basically introductory talk. It's not going to be a very in-depth, but I think we have some time for discussions that we should be fine too. So first, let's talk about the new generation of geostationary sensors. So everyone recognizes this, right? Familiar with MODIS or VIIRS like satellite imagery, right? So these sensors are like the EOS flagship satellites. They have almost daily global coverage. That means every day they connect net surface or the Earth surface, take a snapshot, right? So obviously we can derive many products from these kind of data, but now things changed. Now we have different kind of data. So this is from the geostationary. Now, the most important thing is, instead of have like snapshot one day, now we have every 10 minutes, we have an image of the Earth's surface. And with that, we can have a lot of information. So that's the new temporal information coming in from geostationary. And the whole point of our project, GeoNEX, is trying to harness or make use of that, such information, right? Okay, so now we don't have only one geostationary satellite. We have a constellation. We have a global constellation. So starting from actually 2014, we have the first one, Himawari 8, launched. And so far, so we now Himawari 8 and 9 is 2016, and then we have GOES 16, GOES R 16, and we have the Fengyun Chinese geostationary satellite launched in the same year, and then we have 17 and also the Korean GeoComSat A, right? If it's as planned, the European MTG FCI will launch next year. So we'll have actually near the global coverage by the third generation geostationary sensors by then. All right. So compared to the previous geostationary sensors, I mean, here is just a very simple chart. It says like we have 3 times more channels or bands. We have 4 times better resolution. So now we have about native red band is 500 meter resolution. For visible and to NIR is 1 kilometer. It's a nadir. And now the most important thing still is the higher temporal frequency. Now we have faster scans, 5 times faster. So every 10 minutes for full disk. Now for regional, we have 5 minutes or even 1 minute scans. A lot of information, very high temporal resolution. So these are the spectral bands of compared to the geostationary to traditional MODIS and VIIRS. So now we notice these spectral bands are very similar to MODIS and VIIRS. For instance, we have obviously here we have the red, we have a NIR. Those give us some information of the vegetation, right? And we have some of the sensors have this series bands located at 1.3, about 1.3. So that's for series detection. About 1.6, that's the band for snow and ice detection, I think, because they, snow and ice have absorption in that range. And for 2.2, that's the, I mean, we use this band for aerosol detection. Anyway, so I'm not very familiar with the thermal bands, but anyway, so there are 7 or even thermal bands. I think we can at least use some of those. For instance, for this 10 micron, 11 micron, and 12 micron, those are the split window algorithm for land surface temperature. Some of those are for the water vapor and those things. So anyway, so we have 16 bands, and every 10 minutes, 1 kilometer resolution. That's a lot of data, and let's make use of this data. Okay, so now geostationary sensors obviously have very unique geometry in terms of sound target sensor, right? So the satellites rotate with Earth. So if you stand on the ground, the geostationary sensor is basically fixed related to you, right? On the right-hand side, this chart. For instance, the GOES, I mean, this is probably San Francisco. For GOES, it's always be in your southwest for us. Now, GOES 17, which is GOES west, will be west-south or southwest, right? At the same time, the sun goes by at every time step. So this is actually quite different from sun synchronized or the LEO sensors. So LEO sensors, sun angle is pretty much the same, but the view angle changes. In our case, for each pixel on the ground, you have fixed the satellite angles, view angles, but the sun angles changes all the time. So that's different. And also, this is how the sensor scan the surface of Earth. It's not continuous. This is called playlist. So they have several targets. So obviously, the largest one is the full disk. And for GOES, they have USA, coldness region, and there's a mesoscale, some like hurricane and some hotspots they want to measure, monitoring. So it's not continuous. That means in that 10 minutes window, for each pixel, the sun angle is actually not continuously calculated. So if you really want accurate acquisition time for each pixel, you need some algorithm, right? Okay, so now this is what shows a full disk scan generate about 1 gigabyte of data. It's compressed. So that means about 144 gig a day or 50 terabytes a year. So now how many sensors we have? We have GOES 16, 17 Himawari, GComSat 2A, 4 already, and also MTG. So that's going to generate a lot of data. And because on top of that, we're going to generate products, right? So every time you generate products, it's going to double or even triple the volume. Okay. So now with this incoming observations or measurements, let's talk about how we plan to process them. This is actually more like a conceptual product pipeline. It's a plan. We're still trying to build it. So it follows the traditional NASA satellite data processing workflow. So basically, you take the raw data from sensors and actually NOAA and also operational agencies that's processed them to some level, they call level 1B. And we take the level 1B and reprocessed to improve a little bit. I'll talk about it. It's called L1G. Okay, with that, L1G has the TOA, top atmosphere reflectances and brightness temperature. So we took those things and do Ames correction using a MAIAC algorithm and try to generate level 2 surface reflectances products. And those can go into downstream algorithms to generate level 3 or 4 application data like NDVI, LAI, GPP, NPP, those things. All right, so that's follow the workflow. And on plan, we're going to archive those data on our system and also distribute through a different. Here I shows on public cloud, AWS, and also NASA DAC. All right. Okay, so now I have been focused or emphasizing we want to do global data sets. So that's why we have to pick a global common grid. So this one is, we decided for our GeoNEX global products. So it's very simple. Geographic projection, starting from 180 west longitude and all the way to around the globe to 180 east, right? So because of the focus or the coverage of geostationary, we cannot go very high latitudes. We stop at 60 degrees north and 60 degrees south. Here also shows the coverage of this sensors, the current sensors. And obviously, as because of the very unique view geometry, so when you go to the edge of your coverage, the spatial resolution decreases. I mean, each pixel, let's say native is 1 kilometer and becomes to like 2 at maybe 40 degree north, south. So here shows. So far we're actually missing MTG in the European. So next year, if we have that one, we have pretty much global coverage. Still in the Middle East, there's a little bit coarser resolution. So maybe we can have I don't know if there's going to be a second MTG or MTG East will cover that. So have a global common grid. This is actually, it's also convenient, not only for geostationary, it's also for, we can project existing polar orbiting satellites like MODIS and VIIRS into the same grid. So that will help us to, do this geo-LEO synergy. So we can conduct, inter-satellites comparison and trying to, calibrate our sensor or provide information to each other. That's the plan. So and also that's to us probably the advantage for this common grid. All right. Okay. So actually, let me go back. So because we want to put all different data from different sensors together, we have to make sure every sensor at the right location at each time step. That means we have to do this geolocation correction correctly. So the NOAA and also GMA, this operational agency, they provide some sort of geo-registration correction already, but unfortunately there's some residual. There are some residual errors, so we have to detect them and to correct them if they are. So for this one, for instance, this is from GOES 16. On that day, there's an anomaly of the gyro sensor on the satellite, so they generated some large geo-correction errors. Actually was detected by us. So what we do is we use this SRTM-DEM as a reference data. We choose the coastline and trying to do some basically correlation type of detection to see if the data acquired by the geostationary is actually shift, or there's some location shifts, right? Algorithm is very simple. It's basically called the phase correlation correction. It's just you turn those things into the Fourier space, the frequency space, instead of doing this in time space, and just do some correlation, it will actually show how much you need to shift. For instance, on the left-hand side, those are the arrows shows how much you want to shift west or how much you want to shift north, right? So that's the algorithm tells us for each line of those the scans, how much you want to correct. And this is what after the correction. So if you look at on the right-hand side, this the image is a little bit dark, I know, but you can tell now it's much better compared to the coastline agreement between those imagery and with the if you compare the previous one. The previous one, the shift was like several pixels, that's obviously, right? So it's getting better. In addition to that, another thing NOAA or GMA didn't do is the elevation correction, or another way to call it, probably it's called the topographic correction. So basically, they don't take into account about the elevation variance effect on the imagery. So without the elevation correction, you will see this, for instance, in mountain area, Lake Tahoe will be a few pixels off. So that's actually quite important, because if you want to detect fire, for instance, a few pixels off, that means several kilometers off, right? And also for snow, those monitoring those things, this is actually important. So we used a very simple algorithm to implement this elevation correction, which give us, I would call it decent results. It's not the best, but for our simple algorithm, that's actually good enough. As a first step, it's reasonable. All right. Now, those are just the correction. Now, there's another very important aspect, which is the radiometric calibration performance, right? So we don't do radiometric calibration. The operational agencies do, but we can check and see how the results are, right? So here, the question is, how do we actually compare? How do we compare geostationary, the radiance you measured, or the BRF you measured, with MODIS, right? The problem is because now they have different sun, target, satellite geometry. So to compare them is not very straightforward. So one way to do it, obviously, you have to match. You pick the pixels, actually match with the same geometry, which is called the ray matching. You pick, but it can be only very few pixels, and also you can only do this in the tropics, right? Because on mid-latitude or even somewhere else, you don't have that same view angles as MODIS or as VIIRS, right? Another algorithm developed by the Japanese scientists is called the relative azimuthal angle matching. So it's still, because we cannot actually matching the view zenith angle, we're trying to at least match the azimuth angle. So that's another way you can do it. Now the third way is you use models. So you use BRDF models, for instance, from MODIS, and trying to correct whatever you measure from the geostationary and correct them into the geometry you wanted, for instance, at noon or at some specific solar zenith angle or view zenith angle. And here is the results from a paper by Alfredo's postdoc. So if you compare these, I mean, this is the black line shows HI daily without BRDF correction, and the orange line shows the corresponding data with BRDF correction. If you compare them, you see actually the BRDF correction improves in comparison between these things, especially for EVI. NDVI is actually pretty robust to the changes in sun angle, sun and view and geometry. I mean, obviously there's some theory behind this developed by Yuri. So there is a paper probably, I don't know, or I forgot, it's 2000s, around 2000, there's a paper about that. So if you're interested, you can go find the paper and read. Okay, so BRDF. So as we said, for geostationary data, your view angle is not changing, but sun angle changes all the time. So every time step, you have slightly different geometry, and you compile them together. You actually have some samples in the different the angular space that will give you some information of the surface BRDF. On the right-hand side, there's time series. That's interesting. Compiled over, I think it's one of the Fluxlet sites at Amazon. So you will see, you actually capture those hotspots effect, which is very interesting and very exciting, because this is probably the first time I see this hotspot effect from remote sensing data, from satellite remote sensing data. And the bottom panel shows NDVI, corresponding NDVI. And as, again, you can see NDVI is pretty robust against those angular changes, right? So those are proved in theory, but now it's quite interesting to see it with data. Now with this NDVI, how do we actually measure it, or how do we actually use those NDVI information? Here is the shows the MODIS BRDF model. So basically, we decompose the BRDF into some kernels. One is obviously an inversion, right? That's the constant. Another one is due to the volume scattering. A third one is due to the geometry of the trees. So they have different functions, kernels you can calculate given different, VZ or solar zenith angle, these things, and you can calculate the shape of their functions, and then you can try to fit. You can fit them with the observational data. This is a way to account how the BRDF affects at surface. This is the also the model utilized by this algorithm called MAIAC, developed by Alexei Leopoldstein at Goddard. So this is one of the kernel or core algorithm used by this algorithm for Ames correction. So we're going to talk about it later. Okay, so let's talk about some preliminary products. I mentioned MAIAC already. So I think MAIAC stands for multi-angle I forgot what I is. But anyway, AC is Ames correction, I think. So this algorithm takes time series of observations with different the sun satellite geometry, and using that BRDF model, trying to do Ames correction, and also to retrieve aerosol optical depth of the atmosphere. So it was developed for MODIS. Now we're actually adapting this algorithm for GOES and also Himawari, basic geostationary, and we're trying to see how much we can improve, or at least achieve the same results as MODIS. I think we can improve. That's my belief. Anyway, so now with this Ames correction, we have surface reflectance and we have AOD. Once we get there, I mean, obviously we can do NDVI or EVI, whatever. So that's vegetation indices, very robust data to use. This is actually real-time fire detection. So basically, we did develop this as as a model, or actually for really near real time with latency time about 2.5 minutes. That's just a couple minutes. So what happens is NOAA pushed the data. Once they receive the data from the satellite, they push it to AWS, the public cloud, and we set up the whole mechanism. Once the data arrives at AWS, they will send us notice, and then we just launch our server or the machine. We actually use the Docker container and just launch that virtual machine and then process the data. Once we get the notice, we process data and post the results within 5 minutes, which is very cool. I think Jun is is in the audience, so he was the main person actually working on this project. Obviously, the drawback is it costs money, so for that reason, we actually stopped after about 1 year. But the Docker container is there, so we can turn it on anytime if there's a request. All right. Okay, so that's all right. So given all these things, I think to me the most important feature of geostationary data is the high frequency. So temporal resolution. So with this, I mean, here it just shows we have more data over the tropics, so we can have better cloud-free observations, right? So it's because you have more, every 10 minutes, you have a better chance to peek through clouds, even in cloudy tropics, right? But there are actually some interesting, I recently, actually, this is something I'm really working on recently. So here are some time series at two sides. So just compare them, left and right. So these two sites are located in, one is in mid-latitude, another one in the tropics. So I mean, can anyone from the audience can tell me like which one is located in the tropics, which one's in the mid-latitudes? I mean, this is virtual presentation, so it's hard to hear the feedback from the audience. But anyway, so it's actually very obvious to our eyes, right? So the left eye and the left side, the side one must be in the mid-latitudes, and side two must be in the tropics, because when you look at the smooth diurnal change, you know, this is pretty clear, pretty calm air. But when you look at the right panel, you see those up and downs of these signals. You know that the atmosphere is not stable, and there's a passing cloud, and everything is changing, right? So even from pixel level, these things actually provide us with information to tell us something about atmosphere. Actually, indeed, I can use this to derive or develop a very simple index to tell if this is cloudy condition or not. So just based upon how smooth the BRDF changes over a diurnal cycle. So that's actually pretty cool. So I didn't use any of those brightness test, any of those NDVI stuff. Just simple look at the time series, 1 pixel, no spatial information, pretty decent. So that means information is there. We just need to find or develop some algorithm to take them out, to use them, right? Okay, so let me talk about community engagement. This is our website. Our data are available publicly. You can go to our website and read about it and how to download them. This is for TOA. We're still working on the Ames correction algorithm, so hopefully we can provide those surface reflectances products in the near future. And we also organized the special issue on remote sensing. So it's basically over. We have connect 17 papers on a whole range of topics, including machine learning. So it's very very exciting to see how the community has responded to our this special issue. And also, this is for the coming AGO fall meeting. It's going to be online, virtual, but we actually organized last year, and this year we continue. This is the second year we organized a session on geostationary Earth observation. So we connect about 40 presentations. So we have 3 sessions. So this is for the coming AGU. Okay, so that's about what I'm trying to talk. So here are some summaries. So basically, the new generation of geostationary sensors provide new opportunities for land monitoring, for not only land, it's actually Earth monitoring, right? And also provide exciting opportunity for the community to work together. So if you have some good idea, you can contact us at NEX, so we can try to prototype your idea or see to generate some product. The last one is this is our group. So located at the building 566 at NASA Ames Research Park. Unfortunately, I haven't gone back to the office for almost 6 months or maybe more since March. So hopefully we'll get out of this COVID-19 mess and everything will go back to the right track. With that, I'm going to stop and take questions. Thanks.
Yeah, thank you, Weile. We have time for questions. We actually have till 5 and however long we want to stay on. So I think everyone, all the participants can unmute themselves, but please let me know if that's not the case by chatting, sending a chat message.
I had a question. Hi, thank you so much for your talk. That was wonderful to listen to.
Sure.
I was curious from the cloud computing side, both, how are you guys thinking about delivering that data, and how does that relate or link to data standards? What type of data standards are you guys thinking about for imagery delivery? I'll take my question offline. Thank you.
So you talk about this FIRE, near real-time processing, or?
Sure, that FIRE or any of the other data streams you guys might be serving.
So we actually, the idea is this. Actually, I talked with Ram the other day about this. So currently, we are processing GOES, Himawari data all on NEX. So that's a NASA supercomputer located at Ames. But we can push our data to AWS. So the idea is we cannot have a permanent data archive on AWS because that's costly, it costs too much money. But what we can do is we can set up a loop. So let's say we put 2-month data there, and when we have the new 2-month data, and we just erase the older data. You see what I mean? So it's just keep doing that to remove the old data and push the new data. So people that would be easier for people to access whatever products we generate. So that's one option we have there. Right. So processed at NASA Ames, but push some of the data to public clouds. I mean, obviously we have data archive at our NASA supercomputer. It's just have limited bandwidth to download. We recognize that issue. All right.
Great, thank you.
Weile, I got a question. This is Han Kui from SDSU. I joined the meeting late, so maybe you have mentioned this, but I didn't capture.
Sure.
So what is schedule this XYZ's XYZ's project is? I mean, rely on your product. What's the schedule of your release of your product?
That's really hard to answer because really it depends on the Ames correction. The MAIAC depends on how much time UG and Liaposting they can spend on ABI or AHI. Now the latest news is he's going to deliver the latest code, the new code to me next week. So once I have the code, I'll probably test it on our system. It will take probably 1 week or 2, and then I can start to generate the new data. Ames corrected surface reflectances. But to validate these data are really hard. Let me talk about why. So the problem is when they actually tune the algorithm, most of the time they tune over a certain area. Well, let's say they have the AirNet data available. But when you apply them to some other regions, it's just not always turned out to be the desirable results. So and we don't have manpower to check constantly. So that's the issue. So we don't have manpower because they're busy. They're working on multiple projects at the same time. So that's why what we can do is we generate data. We can share data with the community. Let's say share with you, and then you can use the data. You can analyze the data. You can let me know if you find any issues, so I can feedback those problems back to God.
Well, that will be great if you can share the data before the validation. I mean, we can continue our processing. If we found some issues, we can kind of help to the validation. Not validation. I mean, help to quality or assessment something. Yeah. So
right. That's exactly what we want.
Sure, that would be great. Thank you.
Sure.
Yeah.
Some folks have been asking questions in the chat. I think if you want to unmute and ask them directly, yes. Feel free.
Yes, I can read that out. So first I wanted to thank you for this wonderful talk, and the question is probably very basic because I don't have much of a background with these sensors, but do you have any challenges with interoperability? Because I noticed you showed a large range of sensors from GEOS to the Himawari sensors.
Mm-hmm.
So do you have to do anything specific to map from one sensor to the other when you develop algorithms, or is the radiometric correction good enough?
That's actually a very good question. Yes, they are issues. They are different. Although there's, for instance, both GOES and Himawari are generated by the same manufacturer, right? Harris, the company. But they are different. When you look at those bands, GOES do not have the green bands. You see here, GOES do not have green bands. Actually, when we show those pictures, we have to generate green bands based upon blue, red, and NIR. Now, Himawari has the green bands, but Himawari does not have the series bands. So and even they have the same bands, for instance, the 2.2 micron bands, the bandwidth are slightly different. So they are different sensors. So when we combine them together, we still have to be very careful. So one of my colleague, TJ, so he's trying to develop some machine learning algorithms and to trying to develop this concept of virtual sensors or virtual geostationary sensors. The idea is GOES 17 and Himawari has some overlap. Not much. Let me go find the. Right. So this is 17, and this is Himawari. So on the probably cross this 180 this latitude, we have like a few tiles overlap, but it's over oceans, many over oceans. So we can use tiles overlap to calibrate them and trying to figure out their how good they are matching each other. So that's one way we can do. Another way is just do a geo-LEO comparison. So we use MODIS or VIIRS as the third reference. We compare them separately to the same sensor, and then to try to figure out what difference they are and how do we actually converge them together. So hopefully we can, what we want to do is we actually can generate, right now the sensors has 16 bands, but depends on the agency. They actually choose to keep some bands and drop some other bands, but we can actually probably generate 17 or even 18 bands based upon, basically take the unit of their band configuration and generate this virtual sensor, generate from this machine learning approach. Hopefully, so that's one way. And how do we actually create this global uniform or consistent data? So yes, we have to address this question. If you compare the KMA, the AMI sensor, it's also different because AMI actually drops the 2.2 micron band, which is going to be a challenge for us because we use this band for aerosol detection. Without this band, it's going to be a little bit hard. Yeah.
I see. So there's some like hyperspectral type mapping also that needs to happen.
Yeah.
Right?
Yeah.
Okay.
Yeah. If you compare them to now, that's basically because they have different wavelength or the band response function, right? So use hyperspectral data, we can actually estimate. There's some basically scaling factor between each band, even they have the same band, right? Because the spectral response function is slightly different. So that's the traditional way we do these things.
Okay. And maybe this is a separate question, but is there a reason like we don't have more bands? Are there technical limitations to how these sensors are built, or because they have to be placed at such a high orbit?
I think that's the cost.
I see.
I think
that's always the limitation.
Yeah, that's most of the time it's cost. You would like more bands, right? Hyperspectral sensor is coming. Now there are so many of them. For instance, on ISS, the International Space Station, now you have history, you have thesis. NASA is developing this sensor called SPG. It's still in the study mode, but it's coming.
Yeah, I think I know a commercial company called Pixel with 2 X's that are trying to launch a hyperspectral constellation also. So maybe, hopefully it will be useful. Right. I think there's another question in the chat from Ray. I think the question from Ray is, do you anticipate any useful payloads hosted on commercial GEO comm satellites?
Hold on, where's my screen? Okay. I think there's a mission that's virtual, well, venture class. It's called GeoCorp. I don't know if you heard about this name. It's from NASA. It's founded, its PI is Barry Moore at the Oklahoma University. This venture class, Earth and venture class, I forgot, EV2 or something, I forgot the name. So it's basically, they're gonna take the OCO2 type of sensor and mount it on a commercial geostationary communication satellite. It's gonna be located right above Amazon and to monitor or to measure the carbon fluxes in that area. Yeah, there's another one. It's called Tempo. It's focused more on the ocean part, I think. Yeah. All right. I don't know if that answers your question, but that's the information I know.
Yeah. So Mike has some family issues, so he has to leave earlier. So I'm taking his role and moderate this webinar.
Okay.
In the next few minutes.
Yeah.
So, any questions from the audience? So, Weile, I have one.
Sure.
That so yeah, I think probably a big challenge for the users to use the geostationary satellite data is a huge volume of
data volume,
the data set, right? The data volume. So you
Yeah.
demonstrate that GeoNEX platform and probably AWS may be a solution. So I mean, for the for the normal or generalized users, do you have any suggestions of where to download this data and how to use this data? Yeah.
I think for now, if you want to use the product we generated, so it's, can you still see my screen? I know this is, oh, okay, you still can see it. I think this is the web portal, GeoNEX web portal, data portal. It's hosted by Ames or NEX. So you can download the TOA from the site. Now, because of the data volume, my suggestion is, or my recommendation is, so you first locate the area you're interested and just trying to download a few tiles. Remember, like in our case, our common grid, that's 6 degree by 6 degree tiles. So you just download a few tiles, but with all the data for those tiles, because the most important feature of the geostationary data is the time sequence, right? You don't want to miss that. You don't want to just take the snapshot, because if you take just snapshot, it's no difference from MODIS. Maybe it's worse. No difference from Landsat, but you have coarse resolution. But the really important thing is to download all the data, time stack, but for those a few tiles, and that will help you to get some experience with geostationary data. That's my personal recommendation. I think for how to start with, we are going to, if not done yet, we're going to provide some tools, software tools, basically written in Python, basically Python script. So you can directly use those tools. In our case, for instance, to visualize the data and to extract time series. If you're interested in some point, you can extract the time series, and you can do maybe some basic analysis as I showed here. For instance, to do composite and to calculate NDVI or EVI, those things, or even to show something like this, right? To show the BRDF stuff. So these Python scripts are available. So we're trying to provide them as a module, so you can use them directly. So far, we use Python because it's just open source. It's free. Yeah.
Gotcha. Yeah, a following up question is actually because I saw it's pretty amazing that those data can significantly reduce the clouds, as it showed in one of the slides.
Right.
But NASA or other agencies have any plan to produce a higher level GOES data set, or the product that can facilitate analysis for like seasonal analysis or even longer time scale?
Yeah, so so I mean, they just had this geostationary call, right? Geostationary call. So so people are founded to do something. For us, like Xiaoyang is going to do philology, right? and there are some others. But the, we actually haven't got the funding to do, especially for those low downstream products yet. But we are trying to, we're going to do the prototype. So with our own NEX funding. So that's our strategy. In the long term, if, I mean, today I'm just talking about the products generation, but we haven't talked about science. If we can actually generate good science from this data, for instance, if we can use this data to detect, seasonal change over Amazon, to detect some, very interesting flux, carbon flux or water flux in some critical area, or to monitor disaster. I think the headquarters will be interesting to fund the community to keep this data going. Now the key is because these are operational satellites, right? So we know in the next, it's not just a few years, in the next 20 years, maybe 30 years, we will have this data available. So, and this data will be archived. So think about it, it's just like this data will be there, have this every 10 minutes data over the Earth for 20 years. It is going to be the records of the planet. So we can, at some point, we should be able to, make use of this data and for science, right?
Yeah, excellent, thanks.
Money is always an issue, but science. Okay.
Yeah, I totally agree that given the time, we'll, at some time point, we will have the data available.
Yeah. So I mean, to me is because for optical remote sensing, you get information from either spatial resolution, right? Spatial dimension, you have information coming in, or you're from spectral, which is hyperspectral sensor is about. So, and now another way is this temporal resolution, or temporal time series information, which is unique, kind of unique from geostationary data. So with that, if we can make good use of all of them, we should be able to do some good science. Let's hope for the good.
Yeah.
I have one quick question.
Sure.
In the beginning of your talk, you mentioned something like we will or we can put some of our products in one of the NASA DACs.
Yeah.
I was wondering if there has been any discussion about it with NASA headquarters.
No.
No, okay.
The thing is, I mean, I know only a little about these things. So far, our data are hosting on NAS. In the past, we talked to NCCS and Goddard. So if they wanted this data set, they call this is called like PI-led science data sets. So if it's officially funded by the headquarters, then I will have better way to talk to the DAC and host these data. But there's some other stuff. It's just the commercial sites, for instance, AWS. Now they actually host a lot of these data sets, right? Maybe there's potential in the future we can actually host more data directly on the public clouds. It's possible, because the money is it's a lot for us, but it's probably a very small amount for them. So it's easy for them to do it if they can actually attract use from the user side. I think there's maybe some commercial opportunity to use these data sets anyway.
Okay, thank you.
Sure.
So we have 1 minute left. If I'm not sure if there's any other questions from the audience. We can, I think Weile can answer one. Or, one question? If no, we can stop here.
Yeah, let me actually stop here. I think that's good enough. It's a quiet afternoon, so
Yeah. Okay. Okay. Let's thank Dr. Wang for his excellent talk and sharing his in-depth view of the GeoNEX and the geostationary satellite data and science. And thank you everyone for joining this webinar. And I think we look forward to your participation for our next webinar, which I think is October, in 1 week or 2 weeks. I don't quite remember.
8th and 15th.
8th and 15th. Okay, 15th. So in a week. It's 15th. Okay, yep. In a week. Okay.
All right. Thanks, Ming.
Yeah. Thanks, Weile. Thanks, everyone.
Yeah.
Thank you.
Bye-bye.
Bye-bye. Hi, Rose. Can you hear me?